Welcome to another devlog for my still unnamed programming dungeon crawl management game. I was traveling for a chunk of this week, so this devlog is going to be a little bit different. I'm going to do a semi-live demo of writing an agent AI in Rust using the game's low-level WebAssembly API. But first, if you're new, this is a game about controlling a group of characters as they explore dungeons and bring back loot, which you use to upgrade the town, which makes the adventurers more effective, etc. Rather than focusing on high-level management of pre-designed AI characters, the core game is about programming the characters yourself using a graphical programming environment, or, for the truly adventurous, and this is what I'll demonstrate today, a low-level WebAssembly API. Players will be able to play the game solo locally or upload their AIs to a server for asynchronous multiplayer competitions. The whole point of this project is to capture the unreasonable excitement of writing little toy simulations and watching the agents live out their simulated lives. But, as a game. Okay, so here's my setup for this demo. I have the game running, I have a little shell script which is going to recompile the AI as I make changes and hot load it into the game, and then the console output for the game itself in case we need to look at that for some reason, debugging or whatever. And then I have the code for the AI, and I'm going to spare you the setup for this project. It's not too complicated, but this isn't a tutorial, so you don't need to see that part. And so what I've got here is a basic framework for one of these AIs in Rust. And I'm not going to do too much detail on the Rust, so if you're not familiar with the language, I think you'll still be able to follow along, but the syntax may look a little cryptic. So what this is it is a WebAssembly component implementation, and I'm using Wasm Time WebAssembly stuff, if that's useful. And so the way this works is there's a set of bindings out to a WebAssembly component definition file, which I'll pull up. Looks like this, and this just this just describes all of the types and exported and imported functions that the WebAssembly component will need to understand in order to interact with the host, which is the game in this case. And so there's a bunch of types that describe various game objects that the AIs need to be able to interact with. And then there is a couple of exported functions. This is not super organized right now. And of course, not documented at all because I'm the only user, but all of that will change. So there's a couple of exported functions. Editor config is, we're not going to worry about that, but step is the main one. So this is the game's entry point into the AI. So every turn it will call this function, and the AI is expected to return a command, which will be executed by the game. So if we go back to the actual code for the AI, you can see I've got an implementation of that function here inside this component struct. So this is where all of our code for the AI is going to go, and everything else that the AI does, again back to the component definition, is going to be by calling these query functions, which get various different bits of data about the game. So the AI can ask what tile is at a particular location. It can ask for a list of all the tiles that it can see in the world. It can ask what creatures at a location. It can ask for information about itself. It can ask for all the creatures it can see. There's some that I'll probably remove, like nearest creature. The AI can do that calculation itself, so that's probably not important. Similar things for items that are on the ground. Some information about the character themselves. So there's a bunch of these query things, and the AI will call those functions, get data from the game, operate on that data, and then return a command that does something. So currently this is just a dummy. It always returns the null command that does nothing. And if we go back to the game, you can't really see what I'm doing, but I'm taking turns by pressing the space key, and nothing's happening. The AI is doing nothing, and that's expected. So if we quickly make it do something, so I mean, first off, we can just do a debug print. So now every turn, the AI will print test to the console. So if you look here is where the console is, and when I take a turn, you can say first it hot loads the AI, and then there's our test. And every time I take a turn, it prints another test. So we can see the AI is running. Fantastic. But that's not very interesting. So the structure here is that the AI needs to know what actions the character is capable of taking, and that's determined by what equipment the character has equipped, or a set of intrinsic actions. Like the AI can always walk around, regardless of what its equipment is. So there's a few intrinsic actions like that everyone has. You can always pick up stuff off the ground, regardless of what equipment you have. But everything else, like attacking with a sword or whatever, that's supplied by equipment, and those actions will only be available if you have that equipment equipped. And so I've got a couple of helper functions here that I've already written. So the AI can call this action function, which will return a list of all of the actions that the AI can perform this turn. Any action that is possible, not necessarily actions that will succeed. So like if you're standing in front of a wall and you walk into the wall, that fails because you can't walk into the wall, but that action will still be available. Like you can choose to walk, it won't do anything. So this is a list of all the actions that you could choose, even ones that might possibly fail. And for people who are interested in the doing this in another language, for instance, by working with the Wasm stuff directly, you can look at, this is the definition of that. So this is what we know. We know there's a function called actions that will return a list of these action types, and we can go up and find the action type, which is here, and we can see it's got some data. So it knows what the name of the action is, and then it knows what the sub-actions that it's composed of are, and those are a list of these variations. The variant is equivalent to Rust's a num, if you're familiar with that, or I think in a lot of other languages they're called tagged unions. So I think in C it would be or C++ it would be a tagged union. So it's just a typed structure that can have additional data that changes by what variant it is. So the microactions determine like the sort of the atomic lowest level mechanics that the AI can interact with. So this is like walk in a direction, attack something, and a few others. This list is likely to change as the game matures, but that's what it currently is. And then the action is a group of those that's supplied by something. I talked a little bit about this in the previous video, but like the simplest possible action would be like walk, which has one microaction that is walk. All it does is just bundle that. But a complex microaction might be something that does an attack that does some damage and also applies a buff and maybe even does some more complex things. And it might have several microactions attached to it. And that would be supplied by like an enchanted sword or something that has a more complex structure. In this demo, we're just going to be working with the simplest possible actions. So they'll all be basically one microaction. Okay, so back to the Rust. We can call this to get a list of actions and iterate through that. And we're looking for an action that supplies a particular microaction. So I'm going to call this function, supply it the microaction that I'm looking for. So I say I want to walk, so I'm going to supply it with walk. And then it's going to search for all of the actions that the character has access to and find the first one that supplies that particular microaction and then return its index into the actions array, basically. And then I could do something with that. So let's do something slightly interesting. So we're going to try and walk. So I'm going to find the ID of my walk action. So find action. And then I just want that one. This is a failable function because like I might be looking for a microaction that I don't actually have access to. So like I might want to convert a resource from one type to another. That's a come on, a micro action that I can do, this convert micro action, but that's not in any of the intrinsics. I have to have access to a conversion station, be standing next to a conversion station to do that action. So if I called this with convert, that would fail because I don't have a conversion action available right now. But walk is available in one of the intrinsic actions, so I know that this will always succeed. So I'm just gonna assume that it's there. So unwrap just ignores errors basically. It'll crash if there isn't a walk action, which in this case is fine. So now I know the ID of the action. My intrinsic action is applies walk, and now I want to decide what to do with that, which means I want to return a command that uses that action. And right now I'm returning the null command. But if I go back to my list here, I can find my definition of command. I'm sorry, it is a variant. Okay. And I can see there's actually two right now, which is null and use action. And use action takes the index to the action in my action list, which is what I just got from that function, and then a configuration blob, which has data about what I want to do. So let's do that. Use action, and it's inside a tuple, and so I know that walk ID is my index, and then I want an action target, and that is a variant also. So let's look at that variant. So you can see it has several variations, and the one I want here is just a direction. So I'm configuring this action with the direction because that's relevant for walking. And if I were doing other actions, I might use different configurations. And let's just walk always east for now. Okay. And why are you complaining about that? Oh, I see. Okay. There we go. And there. This is an optional. Okay, so now we've made the types happy, and this has been rebuilt, and now when we take a turn, it will hot load, and we can see that we start walking. And as soon as we hit a wall, we stop because we can't go anywhere anymore. Okay, so there's like our most basic AI. So let's do something slightly more interesting. Let's random walk. So I can just quickly choose a direction, and let's do this. I'm using FastRand, which is just a minimal random number generator package. I'm gonna just pick a number between 0 and 4, and I'm gonna go. So some of this kind of stuff will be, I will be supplying an ergonomic, like ease of use library for doing some of these basic operations in the final version. It's just I haven't written any of that code yet, so here I'm sort of doing it all by hand. But like, likely there will be, or there'll definitely be like an easier way to pick a random direction or something than to have to write that blob. But currently that's how it is. Okay, so now I choose a random direction, cardinal direction. The game is actually 8-directional, but this is just, we'll stick to cardinals for now. And then I pass that into my walk configuration. So now that's recompiled, and we'll hot load. And now you can see if I just turn on the turn clock, the AI random walks. Okay, great. So that is interesting, not super interesting. So let's try and do something slightly more interesting. So first off, let's try and find those apples. So if you look, there's I'm going to take manual control of the AI for a second so we can make that tree go away. So there's these apples in the ground which represent a collectible resource, and let's try and pick those up. So first off, we need to know if there are apples present. So let's go well, actually, first let's say if the AI is on top of any object, let's just pick it up. We'll just do that first. So if we go, actually, I don't care what the item is. Okay, so what that says is I'm going to query the game to tell me what the item, if any, at location 00. And in the AI interface, all locations are relative to the current position of the AI. So 00 is always the current position of the AI. And if you want absolute positioning, you have to take care of that yourself by tracking how you've moved over time. So saying what's the item at location 00, that will tell me what item am I currently standing on. And that will return an option type, which can be nothing or something. So this is, if you're not familiar with Rust, this is basically the equivalent of a nullable reference. So like none is like a null pointer, and some is like a pointer that points to something. So in this case, I'm saying if I can unpack that into a sum, which means it actually returned something, then I'm going to take an action, which means I can pick something up. So I'm going to go find action. And so like walk, I know that pickup is one of my intrinsics, and so that will always be available. So I don't need to worry about whether or not I have it. And if I do have it, I'm just going to borrow this code. And I'm going to use that action. And pickup doesn't require a configuration because it only does one thing. So there's no additional data. So that just says pick up whatever you're staying on top of. And I need to actually do an early exit. Okay. And it is capital U. Okay. So now that says that if I'm standing on something, and I have a pickup, and I know I have a pickup action, I'm just going to do it. I'm going to pick up the apple. So that's my default behavior. So we'll do that check first. And now, I guess I can show that works. Let's do that. So now we've done that, and we reload. And again, I'm going to take manual control of the character because it doesn't know how to walk to the apple, but I can do that manually. So now I'm standing on top of the apple, and if I let the AI take a turn, it picks up the apple. So that's what we're expecting. Okay, pause to fix a bug I found, and now we're back. We want to walk towards the apple. So in order to do that, we're going to get a list of all the items that we can see. So let's just make a list. And if we go back to our definitions, we can see visible items here. It's going to return a list of tuples of locations and the item record. And we want to know which item is closest, because we don't want to just walk around at random. We want to walk towards the nearest thing and pick it up. So we're going to sort these. And the only thing that's relevant to this sort is the location. So we're going to grab that. Sure. So I can do that with right. And I'm going to bring that back down to 32. Okay, so now just the length of that vector sorted, and we're going to sort those in ascending order by default, so the closest thing will be the first thing in that list. So we're just going to walk through that list for the location and the item in items. And we now want to see if this is the kind of thing we want to pick up. So if we go back to our definitions, we can look at the query item, and we know what the name of the item is. We also know if it's what's called furniture. And so in the game, items are separated into furniture and non-furniture. Furniture is things like a tree. That's an item, but you can't pick it up. You can't even walk through it, so it's furniture. Whereas the apples, like what we're interested in, are not furniture. They're things you can pick up. So we're going to check that. So if the item is not furniture, we're gonna try and walk towards it. And we know that location is relative to the character's current location. So we're just going to do a really dumb conversion into cardinal direction. So if x is greater than 0, then it is to the east. If it's less than 0, it is to the west. This is the kind of thing that eventually there will be a more ergonomic way of doing this, like a client library that does this kind of calculation, because this is stupid to write. But I just haven't done that code yet, so this is how we have to do it. And increasing y is down, so south. Otherwise, we're going to just assume it is north. That sort of ignores the possibility that we might be standing on the object, which we shouldn't be, because we should have broken out of the step function at this point if that were true. So this should actually handle all cases. So now we know the direction. And then we also need to get our walk action. And since I'm going to be using that for this case as well as the random walk case, we'll just do that first so that we can use it in both of them. And then I'm also going to reuse this here. And that should do it. So that will, get our items, sort them by distance, and walk through them in order of increasing distance, find the first one that's not furniture, figure out the direction as the crow flies towards it, and then try and walk in that direction. So now we've recompiled, and we should be able to reload, and we can see that the character is now walking towards the fruit and picking it up. And when he can't see fruits, he random walks. And there he's stopped because his inventory is actually full. He can't pick up fruit anymore, and we haven't handled the case. So let's just quickly handle that case. And we're gonna go back to the thing and figure out how I know about inventory. That is in stats, I think. Yeah, so when I get the actor's stats, then that includes the maximum size of my inventory. And I get that stats by calling character stats. So go back here, and we're going to do that. We're going to go, this gets the character stats, and and then we're going to check, we actually want that up here. We're going to check to see if, get my inventory, just figure out how many items are in that. If that is greater than or equal to stats dot inventory size, then I know I just can't pick up any more items. I'm full. And so I just skip this entire branch and go just default to random walking. And I need actually to move this out of that. What is it called? Oh, because some stats can change due to buffs or whatever. We got, not that current, we get the current stats. Just get it to the right type, because Rust, and okay. So now we should correctly start random walking instead of trying to pick up that apple. So we turn the clock back on, and it is not happening. Why is it not happening? Is greater than or equal to... Alright, let's check our inventory size. And also that... if this is, sorry, got that backwards, less than that is what I mean. That was just dumbness. Okay. And so now we can see we start random walking because our inventory is full. So now we've got a, go back out to the more interesting part of the level. Okay. So now that's not super complicated, obviously. You could do a lot more. And you can sort of get this sense that there's a, a fairly rich API here for doing stuff with the game, and that this is going to get larger as the game develops. And here you can use that to do whatever you want using, I'm showing Rust, but this definition can be used from any language that supports the WebAssembly component stuff. Which right now your best bets are going to be Rust or C++ or Go. Also, Python does work, and in the finished version of the game, there's going to be, I'm going to pick a scripting language, likely going to be Python, but I might choose Lua. Haven't really made up my mind yet. That's going to be the main scripting language I sort of encourage people to use, and there'll be some tooling built up around that and some documentation and some client libraries. And then also Rust for people who want that, because that's my implementation language, and it is probably the best supported language for this stuff, both in my code and in like Wasm time. Maybe C++ is equally well supported, but the core stuff is all in Rust. And so there'll be some client libraries and some documentation for us. So those two languages. But then people could choose to do whatever they want. And this stuff is relatively easy to work with. Like, these bindings that I'm using here are auto-generated from this file. Like, I didn't write any of this binding code. And there's equivalent auto-generators for a bunch of different languages. And so you can use any of those you want. Anyway, I hope that was interesting. In the future there will be more elaborate tutorials and more organized stuff and more complex demonstrations as this stuff develops. This was just a quick thing to give you a sense of what the low-level API currently looks like. Again, all of this is prototype, and some things will be the same in the final game, but some things will change. But this is what it looks like currently. So that's it. I think I'm done. Let me know if you like this style. This sort of less structured, less scripted, and I think significantly longer video, a little more technical. And if a lot of people like it, then I can consider doing maybe some live streaming of coding, both of AIs and maybe even of the core game. So let me know what you think. And next week we will be back to the more scripted and more concise update videos as normal. So thank you for watching, and I hope to see you next time.